Hello guys, here we are again with another lecture, and today's lecture we're going to look at design of experiments. I have with me here some notes that I've written down for you guys, so I'm not actually going to go through these notes, so I'm just going to quickly look at what we're going to do. We're going to look what this note is about. This note is just about approaches to experimentation, what is design of experiments, definition of DOE, why DOE, the history of DOE, factors, levels, and responses, and then interaction, randomization, blocking, and replication. These are actually the components of a design of experiment. We're also going to look at the types of DOE. When you look down the notes, we have the types of DOE to be full factorial design. We have one factor at a time. We also have screening experiments, and we have fractional factorial designs. So the purpose of today's lecture is to look at a factorial design analysis in the R software. So I have with me these lecture notes here for your reference or for further knowledge, and I have recommended a book here, this textbook here, for those of you who would like to further your knowledge in this topic. And the book is A First Course in Design and Analysis of Experiments by Gary. And I have here this link here which will actually help you obtain the PDF copy of the book. So it's a very good book and interesting as well. So I highly recommend this for design of experiments, for knowledge in that area. So today's lecture actually is to look at the factorial design analysis in R. So what we're going to do is we're going to try to perform a factorial design analysis in R Studio. So the data that we're going to be looking at is a very short data set. I've already imported the data here into R Studio. I have this data here. Let me make this bigger. Alright, I have this data set. I have 5 variables and then 8 observations. As you can see, it's a very short data set. It's just for the purpose of this analysis. It's just to demonstrate how we can actually do a factorial design analysis in R Studio. So I have run yield, which is the variable of interest. In other words, this will be our response variable, yield. And we have the explanatory variables, or the factors, temperature, concentration, and catalyst. Actually, this run here represents the number of times the experiment is being run. As you can see, the experiment was run 8 times. And this run in our analysis will not play any major or significant role. So we're going to have to get rid of this column here because we don't need it in our analysis. The variables that we do need are these 4 variables: yield, temperature, concentration, and catalyst. And as you can see, every variable has 2 levels. Every explanatory or every factor here has 2 levels. The factor temperature has 2 levels, 160 and 180. We have concentration with 2 levels, one at 20 and the other at 40. Likewise with catalyst, we have 0 and 1 being the levels. So here we want to study, we want to see how these 3 factors, either by itself or interactively, affect the yield or the response variable, that is, which is the yield here. So we're going to quickly get rid of this variable run. We need to get rid of that. So I'm going to call my new data set data1, and then I want to get rid of the data of the first column there. I want to get rid of that. So I run this code here. So alright, so I run this code. Okay, once I run this code here, I'm going to have my new data set data1. So I'm going to view that data here. view data 1 to see whether we've been able to delete or exclude the first column. I'm going to view that. Sorry, I just viewed the original data. I meant data 1. So here. So I have this new data which has only 4 columns, which I was able to get rid of the first column. So now the next thing to do is to actually visualize. Or first of all, before we visualize the data set, we can see here that this variable here has zeros and ones. So what R does is that it automatically considers these numbers, this variable, as a numeric. So I want R actually to consider that as a factor. So I'm going to tell R to consider my variable catalyst as a factor. So that will be the next thing to do. So I'm going to have data. So here, actually what I did here was to, let me put some comments, removing the first column of the data, of the original data set. So now what I want to do is to convert catalyst variable into factor, so that I will not see that as a numeric variable. So that is the reason of doing that. So I'm going to have data, then catalyst, so I'm going to see actually my new data is data 1 catalyst. Okay, I'm going to have that to be equal to factor, and then data 1 catalyst. I'm going to run this code here. Oh, I have an error here. That should be 1A, not double A. So now I have been able to convert the variable catalyst into a factor variable. So the next thing, every analysis you do, is better to visualize your data. So I'm going to say visualize the data. So I'm going to have plot data 1. I'm going to see how the data looks like. So I have this plot right here. As you can see on your screen, I have yield, temperature, concentration, and catalyst across the diagonal of this plot, and how they interact or how they are related. So this gives me a fair idea of how the data looks like, and this will actually inform my analysis in R. So now that we have a visual knowledge of the data, the next thing I'm going to do is to find out whether the factors interact among themselves. So the next thing is to find out whether there is some interaction, because if there is interaction among the factors, we will have to consider that in this analysis. And one thing we need to note also is that in this data set, we don't have any replication, but in most of the cases, or in the real world, you're going to have to face some data sets with a lot of replications, which we have to actually probably use a different analysis or different method to analyze such data sets, or to do factorial design on such data sets. So here I'm going to have a interaction plot. So I'm going to have a M4 2,2 interaction dot plot. Then I have data 1 temperature, then I have data 1 concentration, and I have yield, which is my response variable. Alright, so then I'm going to also have another interaction plot. Since I'm going to have 3 factors, I should have 3 interaction, more than 1 interaction plot. Data 1 should have actually 3 interaction plots. And then temperature, and then data 1 catalyst, and then yield. Now I'm going to have the last interaction plot here. Data 1 concentration, and then I have data 1 catalyst, and then I have yield. Alright, so now I'm going to have to put this in a 1 by 1 array, and through one. Alright, so I'm going to run these lines of code and see what we obtain as the output. So the first one I have here, the interaction between yield and temperature. You could see that as a function, I have an interaction between yield, interaction of yield as a function of temperature and concentration. So how temperature and concentration interact to affect yield, which is a response variable. And you can see that there's no actually the lines in the graph or in the plot do not intersect at any point. As a matter of fact, they are parallel lines and they will never intersect. So this tells us that there is no significant interaction. There is no interaction between temperature and concentration. So temperature and concentration do not interact to affect yield. So that is the meaning. So we now look at the next interaction plot. So here I have the interaction of temperature and catalyst, how the interaction affects the yield, which is the response variable. And as you can see, the two lines intersect at this point right here. So we would say that we conclude that temperature and catalyst significantly interact to affect yield. So we will need to consider this in our model, whatever model we will need to build. We need to consider this interaction here. So we also going to have to, there are formal statistical tests that we could also use, or hypothesis testing, that are also useful in also deciding whether this interaction here can be significant or not. But obviously this interaction is actually significant, so that is how it is. The next interaction plot would be this one right here, concentration and catalyst. They do not interact. As a result, there's no interaction effect between concentration and catalyst affecting yield. So we wouldn't have to bother about concentration and catalyst interacting. So there's only one significant interaction, that is temperature and catalyst. So we can have this. So we've seen the various interaction plots, and we conclude that there's only one interaction, that is the interaction between temperature and catalyst, that affects the yield. So the next thing we're going to consider is, now that we have this knowledge of interaction among just a pair of the factors, we now proceed to so we also have a alternative. Before we proceed, we have alternative ways of plotting this interaction plot. So let me see if I can look at that quickly. Alternative ways of plotting interaction plots. So we have XY plot. Then I have yield. I have data one. Yield, the response variable. And then I have temperature, and then catalyst, and the data is equal to data 1. And then I have a panel is equal to function. X, Y, dot, dot, dot. Then here, I'm gonna have carry bucket here, panel dot XY plot. I have X comma Y. I forgot a comma here. And I have a panel dot LM line. I have X here, then comma Y, then that. Alright, so I have this code here. Let's quickly run this. Alright, so I have this interaction plot. This is another way or an alternative way of plotting the interaction plot. So let's look at this closely. So here I have yield here as my response variable, and then I have temperature. We look at how temperature actually interact with the other factors to affect yield. So this is a different way of actually having this interaction plot. So here we are looking at the interaction between temperature and catalyst. The other variable is catalyst. So you can see here that there is no line crossing. So from the plot there is no line crossing each box, so we can say that temperature and catalyst actually significantly interact to affect yield. So we're going to have to reproduce the same code here, copy this here, and then you paste it down here, and then we're going to have to consider now we're going to consider concentration and catalyst. I'm going to have concentration here, so I'm going to just run this code again, and now we look at this. There it goes. So we look at there's no interaction between concentration and catalyst to affect yield. So this actually looks better than the other interaction plots. So we're going to look at the last one. I'm going to paste it one more time. We're looking at now concentration and catalyst. So we're looking at temperature and catalyst and concentration. Temperature and concentration, yes, that's what we're going to look at. It's concentration catalyst, temperature and concentration. So here should be concentration. I'm going to run this. You can see here alright, so this is how you can alternatively plot your interaction plot. So now the next thing we are going to consider, the next visualization tool we're going to look at are just box plots. So we're going to have to look at box plots. So I'm going to combine various box plots into one graph. So combine box plots into one graph. I have box plots, I have yield, which is the response variable, and then temperature, concentration, then data is equal to data 1. I have my y axis to be equal to percent yield. In my x-axis to be equal to temperature concentration. I have temperature. Alright, so I have to put this in parentheses in inverted commas. Then I have box plot. Catalyst. And I have my data to be equal to data 1. I have my y-axis. Percent yield. X-axis. Temperature. Catalyst. Then I have alright. So now I'm going to run these two lines of code here to give me my various box plots. So here I have so this actually consists of we see how yield and temperature relate or interact. We see how temperature and concentration interact to actually affect the yield. So that is one box plot, and the other one here is simply temperature and catalyst. So we can get actually obtain some information from this box plot. We can say from both box plot we can say that there are no outliers in the data set because the line actually divides the box into almost two equal parts. So there are not any major outliers in our data set, so which is a good thing. So this will go a long way to help us in our analysis or to obtain concrete and reliable results as far as this analysis is concerned. So now the next thing we're going to consider is to now model the main effects of this factorial design. So we're going to now model the main effects. So what I mean by that is that we're going to build models that will actually fit this data set, considering that we have one interaction in an interaction that is significant. So we're going to start looking at just the main effects. We're going to ignore the interaction for now. So let's look at just the main effects. So let's build a model based on just the main effects. So here we don't consider any interaction. So I'm going to call this model 1. I'm going to have lm yield the response, and then I have data 1 So data is equal to data 1. So I'm going to also look at the summary of this model 1. So I'm going to run this and see how the model looks like. So let me look at the summary. Alright, so I have the summary of the model right here. You can see that the coefficients, there are only two coefficients that are significant. Temperature and the intercept are both significant. You could see that the other main effects, concentration and catalyst, are not significant. So this model here has only two factors, one main effect being significant, and the other main effect, the other two main effects are not significant. So here we'll say that only temperature will significantly affect the yield, which is the response variable. So, and we look at the R squared, the percentage of the variation that is being explained is 84%, which is not too low, but we actually would want to have the best model that we get out of this analysis. So this will be our first model. Then the next model we're going to consider is where we have two-factor interactions. So we may have 2, 3, or 4-factor interactions. So the second model we're going to consider is where we have the main effect and then the interaction, and then the two-factor interaction effect as well. So here we're going to consider the interaction here. I'll say two-factor interaction effects in the model. So I'm going to call this model 2. I'm going to have it to be I have yield, and I have this side here to the plot 2, and then I have data is equal to data 1. So now I'm going to look at also the summary of this model 2. I'm going to run this code and then look at the summary. Again, here we have considered two-factor interaction effects. Here we have temperature and concentration. We have temperature and catalyst, concentration and catalyst. And alright, so now you can see that for the main effect we only have catalyst being significant, and we have two interaction effect, that is the interaction between temperature and catalyst, being statistically significant, as you can see here. And our R squared has increased from 84% to 99%, which is almost 100, which is a very good. Actually, we use the adjusted R square most of the time because this gives us more accurate information as compared to the R square. So we have 99% here, which is very good. So now the next thing we're going to consider is to see if we can compare the two models together. See if there's any significant difference between these two models. We're going to see that. So comparing the two models. So this will help us to let us know if there's a significant difference. If there is, then we will have to choose one which is actually more appropriate. So I'm going to say ANOVA model 1, then model 2. So I'll run this and let's look at the results. So I have this to be not significant. So there is no significant difference between those two models. So as you can see, indicated by the p-value here, there is no significant difference. So either model could actually be used as far as the analysis we've done so far is concerned. So now we're going to consider a full model which includes three-factor interactions. We're going to consider a full model of the three, which will consist three-factor interactions. So I'm going to have including three-factor interactions. So I'm going to call this model 3, and that will be yield I have this equal 3, then data is equal to data 1. I'm going to look at the summary of the model. So I'm going to run this and then I look at the summary. You can see here that we have the estimated coefficients, but here we don't have any value here. This is because actually we don't have any replicates in the data, so we have no way of assessing the significance of any of the coefficients of this full model with all interactions. So what we could do here, we could actually model this with some but not all of the interactions present. So we cannot consider the three-factor interaction because we don't have any replicates in our data set. So we're only going to consider the two-factor interactions. So now the next model I'm going to build, I actually found out that two of the two-factor interactions were not significant. So and I also found out that one factor was significant. When you look here, where we had the result of the two-factor interaction, we had this factor here, catalyst, and this interaction, temperature and catalyst, were significant. So I'm going to build a different model which has only these two as the explanatory variables and see how it looks like. So I'm going to call that model 4. So I'm going to call this model 4, and then I have yield, this concentration plus temperature catalyst, then my data is equal to data 1. So I have a summary of this data of the model. So I'm going to run this code here and look at the summary. You can see that now we have every concentration, temperature, catalyst, and the interaction. They are all significant. So this would actually be the ideal model for this data set, because I have every factor here, every coefficient here to be significant, and also my both the R squared and the adjusted R squared are significantly high, which is 99%. So this will actually be my ideal or the best model for this particular analysis. So I can also compare this model with the second model that we have. I have a model 4 and model 2. So I have my p-value to be greater than, which is also, that will be my comparison between the two models. They actually there's no major significant difference, but I will prefer the fourth model because all my terms here are significant. Okay, so this is where we're going to end today's lecture. So this is a brief analysis, factorial design analysis for this particular data set. And like I said, if you need further knowledge, you just visit the textbook that I recommend, and also you can read that for further knowledge. And thank you for your attention.